Well, again, some of these facts were proved in the previous term, and so I'll recall the statements only. But some of them will probably be new for you, and in those cases, I'll give you full proofs. Okay, so suppose that X is an normed space. Now let's recall the following definition. We define the annihilator of a set M in X to be the following subset of the dual. So this is the set of those bounded linear functionals on X which vanish at M. And dually, if we have a subset of X star, then we define the pre-annihilator. The pre-annihilator of a subset M in X star as follows. So this is a set of those points in X for which all functionals from N vanish at X. Equivalent to this is just the intersection of the kernels of all functionals in N. The Russian for annihilator is Annihilator. And pre-annihilator is Predannihilator. It's clear from the definition that both the annihilator and the pre-annihilator are closed vector subspaces. The annihilator is a closed vector subspace of X star, and the pre-annihilator of N is a closed vector subspace of X. We have the following useful result about annihilators. Theorem 1. So this is the so-called double annihilator theorem. So if you take any subset M in X, take the annihilator, and then take the pre-annihilator, so the resulting set is again contained in X, then this is exactly the closure of the linear span of M. Well, the right to left inclusion is more or less obvious from the construction, but the opposite inclusion follows from the Harmonic theorem. If we now try to write the dual statement about pre-annihilators, then in general we have an inclusion only. So if we take the annihilator of the pre-annihilator, then it always contains the closure of the linear span of N. In general, this inclusion can be proper, but if the space X is reflexive, then this is an exact equality. If X is reflexive, then so this is an equality. Part 3 easily follows from part 1. We just apply everything to X star, use the fact that X is reflexive. Well, let's also, by the way, let's also observe a simple relation between annihilators and pre-annihilators. A little remark which explains the relation between annihilators and pre-annihilators. So if we identify X with its canonical image in the bidual, Here little I denotes the canonical embedding of X into the bidual. This is the canonical embedding. So if I identify X with its canonical image in the bidual, then it's more or less immediate from the definition that for each subset n in the dual, the following relation holds. So the annihilator of n sits in the bidual, but if we take the intersection with X, what we get is exactly the pre-annihilator. So this formula shows in particular that if X is reflexive, then we can just identify the annihilator and the pre-annihilator. In particular, if X is reflexive, that is, if the canonical embedding is an isomorphism, then the annihilator and the pre-annihilator of n are the same. So in view of this remark, part 3 becomes a simple corollary of part 1, just a special case. Useful corollary of theorem 1 is the following density criterion for a vector subspace. So suppose that x0 is a vector subspace of X and y0 is a vector subspace of the dual. Then I claim that x0 is dense in X if and only if the annihilator of x0 is trivial. So this easily follows from part 1 here. If it is dense, then the annihilator is obviously trivial, but if the annihilator is trivial, we can take the pre-annihilator of this. And the pre-annihilator of 0 is X. But on the other hand, the pre-annihilator of the annihilator is just the closure of x0 because of this formula. So this means exactly that x0 is dense in X. Next, if y0 is dense in X star, then the pre-annihilator is trivial. This is more or less immediate from the definition. But if, in addition, X is reflexive, then actually this implication is an equivalence. Suppose that X is reflexive, then y0 is dense in X star if and only if the pre-annihilator is 0. Okay, let's now discuss a simple but useful result which describes the duals of the quotients and of the subspaces of X in terms of annihilators. Theorem 2. Again, we suppose that X is an ordered space, and let x0 be a closed vector subspace. So we can form the quotient of X modulo x0 and let Q denote the quotient map. The quotient map. I claim that there exist two useful isometric isomorphisms. First, the dual of the quotient of x modulo x0 is isometrically isomorphic to the annihilator of x0. And explicitly this map, this isomorphism acts as follows. If f is a functional on the quotient, then this map takes it to f composed with q, or equivalently to q star of f. So this turns out to be an isomorphism between the dual of the quotient and the annihilator. And second, the second isomorphism is an isomorphism between the quotient of x star modulo the annihilator of x0 and the dual of x0. So the dual of x0, the dual of a subspace, is isomorphic to the quotient of the dual of x modulo the annihilator. And explicitly then this map acts as follows. If we take an element in this quotient, that is a coset of little f, where little f is a functional on x, then this map takes it just to the restriction of f to x0. So this turns out to be an isometric isomorphism. So this result was mentioned as an exercise in the previous term, in one of the exercise sheets. But we will use it several times in this course, so let me give a proof. By the way, before we prove this result, let me call the definition of a coisometry. If x and y are Norton spaces, and T is a bounded linear operator from x to y, then we say that T is a coisometry if it takes the open unit ball of x exactly onto the open unit ball of y. A typical example of a coisometry, a typical example is the quotient map. The quotient map is always a coisometry. This easily follows from the definition of the quotient norm on the quotient. And why is it typical? It is typical because essentially this example describes all coisometries in the following sense. If we have a coisometry of x onto y, a coisometry, we can take the quotient of x modulo the kernel, and the induced map between this quotient and y will be an isometric isomorphism. So each coisometry is just a composition of a quotient map and an isometric isomorphism. Okay, let's now prove this result. Actually, the first part of this result is just a special case of the universal property of quotients. Special case of the universal property of quotients. So the universal property states that for each normed space Y, we have an isometric isomorphism. An isometric isomorphism between the space of bounded linear operators from the quotient of x modulo x0 to y, and the space of those bounded linear operators on, from x to y. that vanish at x0. Now this isomorphism takes each bounded linear operator S from here to here to S composed with Q. So this is the universal property of quotients, and if you substitute here the base field K instead of Y, then what we get is exactly part 1 of theorem 2. Part 2 is, well, it is not exactly a special case of the universal property, but it easily follows from the universal property together with the Harmonic extension theorem. So to prove part 2, let's consider the inclusion map of x0 into x, as denoted by J. Inclusion map. And let's consider the dual map J star from x star to x0 star. So in this case, the dual map is just the restriction map. It takes f to f restricted to x0. So clearly the kernel of J star is just the annihilator. This is the annihilator of x0. So we can draw the following picture. This is our restriction map, J star. This is the quotient of x star modulo the kernel, that is modulo the annihilator of x0. And here we have an induced map between these spaces. Now, the Harmonic theorem easily implies that J star is actually a coisometry. Harmonic theorem implies that J star is a coisometry. Well, indeed, each bounded linear functional on x0 can be extended to a bounded linear functional on x with the same norm. And this easily implies that the image of the open unit ball in the space under J star is exactly the open unit ball in this space. So J star is a coisometry. And it's a general fact about coisometries. Here it is. That after we quotient out the kernel, we get an isometric isomorphism. So if we apply this picture to this concrete situation, we see that this map is an isometric isomorphism. That's denoted by, say, phi. Phi is an isometric isomorphism. And this completes the proof. Let's now discuss some facts, some relations between properties of linear operators and properties of their duals. The first fact, which is quite easy and which was discussed in the previous term, is the following proposition. Actually, this proposition is a corollary of the double annihilator theorem. Suppose we have two norm spaces, x and y, and the bounded linear operator t from x to y. Then, first of all, I claim that the kernel of T star is nothing but the annihilator of the image of T. This easily follows from the definition of the dual operator. If we now take the pre-annihilator of both parts and use the double annihilator theorem, we see that the closure of the image of T is the pre-annihilator of the kernel of T star. Dually, if we look at the kernel of T, then the Harmonic theorem easily implies that this is nothing but the pre-annihilator of the image of T star. And as a corollary, if we take the annihilators of both parts, and if we recall that the closure is contained in the annihilator of the pre-annihilator, we see that the image of T star, the closure of the image of T star, is contained in the annihilator of the kernel. In general, this is just an inclusion, but in general, this is not an equality. But if the space X is reflexive, then the annihilator of the pre-annihilator is the closure, is exactly the closure, and we get the following result: 5 if X is reflexive, then the closure of the image of T star is exactly the annihilator of the kernel of T. If we now combine this proposition with the density criterion for a vector subspace, which was discussed at the beginning of the lecture, then we get the following corollary. Again, T is a bounded linear operator from X to Y. So the dual operator T star is injective, if and only if the image of T is dense in Y. If we try to write the dual statement, then because of this inclusion we have only an implication, namely if the image of T star is dense in X star, then T is injective. And again, if we assume moreover that X is reflexive, if X is reflexive, then these two properties are equivalent. That is, T is injective if and only if the image of T star is dense in X star. Okay, so this corollary establishes a nice duality between injective operators and operators with dense image. In particular, this is a complete duality provided that X is reflexive. So an operator is injective if and only if the dual operator has dense image, and the other way around. Our next result, this is Theorem 3. It gives us a nice duality between topologically injective operators and surjective operators. So here we assume that X and Y are Banach spaces. X and Y are Banach spaces. And T is a bounded linear operator from X to Y. So I claim that T is topologically injective that is a linear homeomorphism onto its image, a topological embedding, even only if the dual operator T star is surjective. And actually we can interchange T and T star here. So T is surjective, even only if T star is topologically injective. So parts 1 and 2 look similar, but I'd like to stress that they are not equivalent to each other, because we don't assume that our spaces are reflexive. And so Y are not necessarily reflexive, so 1 and 2 are, so both parts are essential. They are not equivalent to each other. And as a corollary, we conclude that T is a topological isomorphism. T is a topological isomorphism, if and only if the dual operator, T star, is a topological isomorphism. By the way, part 3 can be proved independently of parts 1 and 2. And actually we discussed this result in the previous term. But at this point we will be mostly interested in parts 1 and 2. And of course 3 is immediate from 1 and 2. Okay, let's now try to prove this result. First of all, we prove the left-right implication in part 1. So we assume that T is topologically injective, and we will show that T star is surjective. So let's draw the following picture. This is our operator T from X to Y. So we factorize T through the image of T. Let's denote this operator by T0, and this is just the inclusion map. J is the inclusion map, and T0 acts by the same formula as T. Let's now look at the dual picture. X star, Y star, the dual of the image of T, T star, T0 star, and J star. Well, T is assumed to be topologically injective. This means exactly that T0 is a topological isomorphism. T0 is a topological isomorphism. The dual of a topological isomorphism is also a topological isomorphism. So this implies that T0 star is a topological isomorphism. So this is a topological isomorphism. But what do we know about J star? Well, we have already observed in the proof of theorem 2 that J star is a co-isometry. J star is a co-isometry. In particular, J star is surjective. Each co-isometry is surjective. J star is a co-isometry, so it is surjective. And if we now look at this diagram, we see that T star is just the composition of a surjective map and an isomorphism. So T star is surjective. Okay, so we have the left to right implication in part 1. If T is topologically injective, then T star is surjective. Now, before we prove the opposite implication, We look at part 2, and we prove the left-to-right implication in part 2. This will be more convenient. So the left-to-right implication in part 2, we assume that T is surjective, and we want to show that T star is topologically injective. Again, we look at the following picture. Now we factorize T through the quotient module of the kernel. This is T, this is the quotient map, and here we have the induced map, let's denote it by T0. Well, T is surjective. By assumption, T is surjective. So we apply the open mapping theorem, and we conclude that T is open. T is open. And if we take the take any open map and factorize it through the quotient module of the kernel, then the resulting induced map will be topological isomorphism. T0 is a topological isomorphism. And now we look at a dual picture. So this is X star. This is the dual of the quotient. And here we have the dual of Y. So this is T star, this is Q star, and this is T0 star. Well, T0 is a topological isomorphism. This implies that T0 star is also a topological isomorphism. T0 star is a topological isomorphism. But what do you know about Q star? Well, let's recall Theorem 2. Theorem 2 implies that Q star is actually in isometry. An isometry onto the annihilator of the kernel. Theorem 2. This was proved in Theorem 2. And now we look at this picture. So T star is the composition of a topological isomorphism and an isometry. And clearly the composition of a topological isomorphism and an isometry is topologically injective. T star, which is the composition of Q star and T0 star, is topologically injective. And this proves the left-to-right implication in part 2. Now we come back to part 1, and now we can easily prove the right-to-left implication in part 1. So we assume that T star is surjective. T star is surjective. We have just proved that the dual of this operator, namely the double dual of T, is topologically injective. T double star is topologically injective. And let's now recall that if we identify each Banach space with a subspace of the bidual canonically, then T becomes the restriction of T double star to X. T is the restriction of T double star to X, but clearly the restriction of a topologically injective map is topologically injective. And this completes the proof of part 1. T is topologically injective, even only if T star is surjective. Okay, now the most non-trivial part of this theorem is to prove the right to left implication in part 2. To prove that the topological injectivity of T star implies the surjectivity of T. To prove this implication, let's recall a classical lemma due to Banach and Schauder. Suppose we have two Banach spaces, X and Y. Well, actually, it's enough to assume that X is a Banach space, X is a Banach space, Y is a norm space, and T is a bounded linear operator from X to Y. And suppose that if we take the image of the open unit ball in X and take the closure of the set, we suppose that this closure contains an open ball of some positive radius r in Y. So the lemma states that if we have this inclusion, then we have a similar inclusion, but without taking the closure. This lemma is a key point in the proof of the open mapping theorem. So I will not repeat the proof right now because it was already discussed in the previous term. And this is, again, I would like to stress that this is the most essential point in the proof of the open mapping theorem. So in particular, this inclusion implies that T is surjective. In particular, T is surjective. T is open, and so it is surjective. So now we will apply this lemma to the proof of the remaining implication in theorem 3. Proof of the right to left implication in theorem 3. So now we assume that T star is topologically injective. T star is topologically injective. This implies, actually this is equivalent to say that there is a positive constant C such that the following inequality holds. Now this is actually equivalent to the topological injectivity of T star. Now to prove that T is surjective, because of this lemma, it suffices to show that the closure of the image of the open unit ball in X contains the open ball of radius C in Y. If we prove this inclusion and apply the lemma, we will get that T is surjective. So now our goal is to prove this inclusion. Well, suppose that this is not the case. Let's assume, towards a contradiction, that there exists an element y0 in the open ball of radius C such that y0 doesn't belong to the closure of the open unit ball. And let's try to deduce a contradiction. Well, y0 is not in the closure, so this implies that for suitable positive epsilon, the epsilon neighborhood of y0 is disjoint from this set. there is a positive epsilon such that, well, the statement can be written in the following way. So the fact that y0 doesn't belong to the set means exactly that the epsilon neighborhood of y0 doesn't intersect the image of the unit ball. It's disjoint from the image of the unit ball. Okay, let's now do the following trick. Let's form the so-called L-infinity direct sum of x and y. So by definition, this is the direct sum of x and y equipped with the following norm. So the infinity norm of a pair of an element in the direct sum is just the maximum of the norm of x and the norm of y. So we take this space and we construct a map. We define a map from this direct sum to y, as denoted by sigma. By the following formula. It takes xy to tx plus epsilon y. So what can we say about this map? It is clearly bounded and surjective. Sigma is bounded and surjective. It is surjective because epsilon is strictly positive. It is surjective already on the second summand. So we can look now at the following picture. This is sigma, this is y. Here we can consider the quotient modulo of the kernel. So the induced map is a vector space isomorphism. This map is bijective. Actually, it is a topological isomorphism. But it is not an isometric isomorphism in general. So now the trick is to make it into an isometric isomorphism by defining a new norm on y. So let's introduce a new norm on y, denoted by the symbol. Let it be the quotient norm on y, induced by sigma. In other words, this is the norm of this space, the norm on y, which comes from the quotient norm of this space. So let's write the explicit formula for this norm. It is the infimum of the norms of all the preimages of y under this map. So if you now equip y with the quotient norm, then it becomes isometrically isomorphic to the quotient. And so sigma becomes a coisometry of the direct sum onto y equipped with the new norm. This is a coisometry. Okay, let's now take the open unit ball in y with respect to the new norm. Let's denote it just by B. The open unit ball with respect to the new norm. So since sigma is a coisometry B is just the image of the open unit ball in the direct sum. But what is the open unit ball in the direct sum? So we look at the definition of the norm on the space, and we conclude that the unit ball is just the product of the unit balls in X and Y. This is clear because the maximum of two numbers is less than 1 if and only if each of them is less than 1. If now look at the definition of sigma acts by this formula, we see that the image of this product under sigma is the sum of the image of the unit ball under T plus epsilon multiplied by the open unit ball in Y, which is nothing but the open ball of radius epsilon. So we see that B is nothing but this set. So by assumption, Y0 is not in the set, so we conclude that Y0 doesn't belong to B. That is, the epsilon norm of Y0 is greater than or equal to 1. Okay, and now the final step in the proof. Oh, sorry, I have to, it's time to finish. But if you don't mind, just maybe I need just 5 minutes to finish the proof. And of course, then we have a break, 10 minutes break before the seminar. The final step is to apply the Harmonic theorem to this space, to Y equipped with the new norm. So we apply the Harmonic theorem to Y with the new norm. And we see that there exists a linear functional f on Y such that, first of all, the norm of f is less than or equal to 1. And at this point, when I say the norm, I mean the norm induced by this norm on Y. So equivalently, this means that f satisfies the following condition. The absolute value of f of y is less than or equal to 1 for each y in B. This inequality means exactly that the norm of f induced by the epsilon norm on y is less than or equal to 1. And such that f of y0 is exactly the epsilon norm of y0. Well, formally this is not the Harmonic theorem itself, but this is the standard corollary of the Harmonic theorem. If we have a norm space, then for each vector in the space, we can find a norm 1 functional on the dual, a norm 1 functional on the space, which takes this vector to its norm. Okay. So what can I say about this functional? First of all, let's observe that it is bounded with respect to the original norm on y. Well, indeed, if we look at this equality, so this is just B, we see that the second summand is contained in B. The second summand is contained in B. So f takes, so this condition holds for each element in this ball, and if we replace it by the unit ball, this implies that f is bounded on y with respect to the original norm, and the norm of f is less than or equal to 1 over epsilon. On the other hand, let's now observe that the first summand here is also contained in B. First summand, the image of the open unit ball is contained in B. So this inequality holds for any element in this set. So for each x in the open unit ball, x, we have the following inequality. F of t of x, the absolute value of f of t of x is less than or equal to 1. This follows from this property of f. Okay, let's now observe that this expression is nothing but t star of f applied to x. T star of f applied to x is less or equal to 1 for each x in the unit ball, in the open unit ball of x. We now take the supremum over the unit ball and we conclude that the norm of t star of f is less than or equal to 1. Let's now come back to this inequality. So this is greater than or equal to c multiplied by the norm of f. So these two inequalities imply that the norm of f is less than or equal to 1 over c. So if we apply f to y0, then we have the following inequality. But the norm of y0, so y0 sits in the open ball of radius c by assumption. So the norm of y0 is strictly less than c. And this is 1. So the absolute value of f of y0 is less than 1. But it is equal to the norm of y0. And this norm is greater than or equal to 1. And this is a contradiction. On the one hand, it is less than 1. On the other hand, it is greater than or equal to 1. And this contradiction shows that, in fact, we have this inclusion, but we have already observed that this inclusion implies the result, implies that t is surjective. So this completes the proof of our result, of our theorem 3. And that's all for today. In the next lecture, we deduce some useful corollaries of this result and apply duality theory to our study of Fredholm operators.